We now have Tobias Fischer from QUT who's going to tell us about some more field robotics.
Awesome. Thank you so much, Matt, for the kind introduction. It's great being here. And today it's my pleasure to talk about visual place recognition using bio-inspired approaches. So in my talk today, I'll cover three key themes. First of all, low power localization. I'll start out with that. I'll talk about enabling tools, just like Josh did with Hollow Oceans. And I'll also talk about underwater perception, surprise, surprise, following Josh's talk. Now, let me talk about visual place recognition for those of you who are not aware with it. So the problem statement is that given a large database of images, the map of your environment, and a new incoming query image, you want to recognize where am I? So you want to find the mapped image in the database that is most similar to the query image. However, if you look at this example here, it's a non-trivial task, right? There are images of the same place that look very dissimilar because the environment has changed in some regard. And also there's similar places, similarly looking places that are geographically very different. Now, robot localization has been studied for a long time, and I just want to give credit to some of the works. It's impossible to give credit to all the works. But visual place recognition has been used as a loop closure component, so Margarita talked about it earlier, and there's been a lot of work around problem framing. There have been incredible advances in the algorithms used for localization and place recognition. Margarita talked about semantics and how it can be incorporated in the problem and why it's important. We've seen novel loss functions, and they've been enabled by amazing new large-scale and diverse data sets. And we've seen an emergence of new scene representations, so Gaussian splats just most recently. However, what we haven't discussed, it's bad news. All of those algorithms have mostly aimed for higher accuracy, and higher accuracy equals better. But if we can't frame them and deploy them in the long run, then they're not useful. So we have to watch out for their energy efficiency. And yeah, that's really like my main message here is that long-term autonomy needs energy efficiency. And later in the talk, I'll tell you a little bit about some of the methods that we've developed over the last couple of years in that regard. Some people might tell you that SLAM is solved, visual place recognition is solved. Tell them you're not asking the right questions and you're not looking at the right data sets. So as one of the many examples where it's an open issue is in underwater robotics, as you can see on the right-hand side. And why is it so difficult? Josh just said there's no GPS. It's basically impossible to obtain ground truth. And things are really expensive to annotate, and it's very challenging imagery. And I want to start out with the third key theme that I introduced. So that's the marine robotics theme. And we've been very fortunate in working with the Australian Institute for Marine Sciences as part of the Reef Restoration Adaptation program. And what they do is that they take the coral spawn and then they grow them in the lab environment. And then the question they're asking is, where should we deploy those ceramic devices that you see there on the left-hand side? So we have to find suitable substrate. And at the moment, there's divers going, and they place those coral devices very carefully on suitable substrate. And they can do that, they can deploy a couple of thousands of those devices. However, with climate change and the issues that we are having in the Great Barrier Reef, our aim is to deploy 3 million devices annually by 2030. So as you can imagine, there's no way that we can just magically come up with more and more divers. So we need to automate this process, and I'll tell you about some of the work in automatically detecting suitable substrate and classifying the substrate and whether we should deploy those devices there or not, and then automatically dispensing those devices from a boat. So that all comes together with place recognition, obviously, as well, right? Because once we have deployed those devices, we actually want to keep track on whether the coral has grown there over time, and therefore we need place recognition in this problem there as well. And we've recently come up with a new benchmark, if you want to check it out, which is aiming towards this long-term place recognition underwater. So one thing that Josh hasn't mentioned is that it's not only incredibly difficult imagery, but also as opposed to Kitty or something on the left-hand side, where each of us can sit down and easily label cars, buildings, etc. in underwater images, most of the time, we need domain experts, marine biologists, to annotate those images. So here we see corals, and there's different species of corals, and we actually want to know which corals are in the image. And that is really expensive and time-consuming. So one of the things that we've been exploring is using foundation models, and I feel like a Keynote those days is not complete without foundation models. However, what we found is that you can't just use them out of the box, and it's really an advantage if you have a human in the loop to label those images. So what happens is that the marine biologist sits down, and they click on the pixel, and then they annotate the class of the coral in this case for that particular pixel. And they do this a couple of hundred times per image in the past. And the work that I'm briefly introducing here enabled you to reduce the number of labels to just a handful or a dozen of labels. So really, we're reducing the point labels by up to 98%. So how do we do it? We've got a domain expert in the loop. We use DynoV2 or one of the other foundation models that you want. And then we can obtain a similarity map between the already labeled pixels in that image and all the other pixels in the image. And we combine that with some kind of distance map to just avoid clustering images in nearby regions. And if you can combine those maps, we can find the region with the lowest similarity to already contained labels in that image and feed that back to the domain expert and ask the domain expert to label this pixel. And then we can use the obtained augmented ground truth mask to just train a traditional semantic segmentation model. So what's the benefit here, right? If you look at this plot, on the x-axis you see the number of point labels required. So the further on the left-hand side we are, the better, because it's cheaper for the domain ecologist. And on the y-axis we see the mean intersection of over union, so higher accuracy there is better. And what we see in our red curve, that's our proposed method, especially for this setting where we have very few labels, we obtain a huge jump in performance compared to our previous methods there. And can actually, if you qualitatively look at those images, obtain similar augmentation masks using just a handful of pixels compared to previously hundreds of pixels. So when I started my PhD, and now it's a little bit of a context change, but really I want to pitch to you and the whole community is that we need more work on enabling technologies and making those really easily accessible. It's not enough to just open source your work if no one can use it. And to introduce some of those works, RoboStack is, if you haven't heard about it, you can use ROS from any device, whether it's your Mac, Windows, laptop, or if you come to my talk tomorrow morning, now you can use it also on your mobile phone, which is really cool, I think. We've also been looking at Visual SLAM, and we recently introduced the VSLAM lab, which enables you using a single command that you can see there at the bottom to recreate the animation there. So you can run multiple or many SLAM methods on many SLAM data sets, and that allows you to benchmark those methods. And then also we've been looking at those techniques where you don't have ground truth available, right? Because there's many settings where you can't obtain possibly ground truth. And we came up with a method which correlates very strongly with the absolute trajectory error without using any ground truth at all. So you can fine-tune your SLAM method or benchmark your SLAM systems where no ground truth is available. So let me get back to this annoying flat battery, right? What do we do about this? We use neuromorphic visual place recognition in this particular example. So what is neuromorphic? It's brain-inspired, right? And to capture you again, to get you back to my mission here, is that we want long-term autonomy, and we need energy efficiency for that. And I think there's a huge potential of neuromorphic computing in robotics more generally. So what are the key components? One of the early components there are spiking neural networks, right? So most of you will be familiar with deep networks. However, in a spiking neural network, the information transmission is very sparse. So you only have those binary signals, and the information is kind of contained in the timing of those signals as opposed to the value attached to a spike. There's an internal memory for each spike. And what is cool about them is that if you have a suitable processor, so specialized hardware, then we can implement really energy efficient solutions. And I want to contrast it to deep networks where any neuron is active at any given time, and it's basically like a add, multiply, and some nonlinearity there. So what are the other components that we need for a fully neuromorphic place recognition system? On the sensing side, many people have been looking at event cameras. If you're not familiar with it, they don't give you absolute intensity information like your conventional phone camera, but instead they only transmit the information that has changed, so the delta in the log intensity of the image. Then we need the spiking networks, and we need a suitable processor. So in this case, it's a SynSense spec. You can go down to the exhibition hall to check them out. And then importantly, we're talking about field robotics, right? We actually want to deploy those algorithms in real time. And just to introduce the neural network architecture, right, compared to a super hundreds of layer deep network, what we've got here is like the most simple network that you can possibly imagine, with just an input layer, feature layer, and then the output layer, which classifies the different places over time. So that's only like 45,000 parameters. You might now ask, how do you actually train those networks, right? The issue is with those spikes, derivative, it's more or less all the time 0, so it's very hard to do backpropagation. There have been some works on approximating backpropagation for spiking neural networks. What we're doing here instead is using a really old algorithm called STDP, spike time dependent plasticity. If you remember your biology class, what fires together wires together. But we are introducing a trick that you can read in our paper, and it's just been accepted to Science Robotics, where we introduce some forced spikes to kind of guide this unsupervised learning process. So the results here, the key takeaway message is that we can achieve comparable performance to conventional algorithms, but consume 20 times less energy compared to an implementation on a Jetson, which I think is really cool. So if you say, oh, but I've got all the energy in the world, why should I care about it? If you don't care about energy, you might care about training and inference speeds. And last year at ICRA, we presented a very similar spiking neural network scheme where we trained a place recognition algorithm within a single minute, and then you can do inference on it in the order of kilohertz. So to sum up, neuromorphic computing, I think, brings intelligence robots where GPUs can't go, from underwater reef restoration to remote infrastructure monitoring. And with that, I'd like to thank all my collaborators, partners, and funding agencies. If you're looking for a PhD, please get in touch, and I'd love to connect with you. Thank you very much.
Okay, we have time for one quick question. Any questions from the audience? And I'm sorry I missed the online ones before, but someone figured out how to use them, so I will keep my eye on those. Question. I've got a question. So, when we're thinking about, power for these sort of mobile robot systems, and obviously this has been a big push now with humanoids because they're very power hungry relative. Do you think some other technology is coming to save us? Is it going to be batteries? Is it going to be, I don't know, solar panels on the back of our robots? Are there ways that we're going to both conserve power but also get more in the short to medium term?
Yeah, absolutely. So I'm not saying that this is the only solution to have more energy efficient solutions. I think it's an interesting one, and there's lots of potential, and I really want to bring it to more application areas as well, just to see where you can have a unified system. But you're absolutely right. There's many other ways that we should look out for. And obviously, it's a question as well on where your energy is actually consumed. Is it in the processing? Is it in the actuation? And that's going to depend on the platform as well.
Awesome. Okay. Thank you so much.